Hi, my name is Earl Cohen. I'm the Chief Architect of the Flash Components Division of LSI Corporation, and we're here today to talk about the LSI SF3700 flash controller and how that controller enables us to support sub-20 nanometer flash in the data center. As we all know, SSDs have shown to have a huge number of benefits, and because of that, a lot of market growth. And the benefits SSDs have over HDDs are many. The only one not listed here is cost per gigabyte. That's still the one area where HDDs are better, but on almost any other metric, everybody wants to move to SSDs. And you can see that based on the growth in SSD shipments on the right-hand side. Now, while SSDs are growing in market volume and market penetration, it's actually becoming harder and harder to build SSDs because NAND flash, the basic storage technology that SSDs use, is becoming more and more challenging. The challenges, in some sense, are caused by the benefits, the lower cost per gigabyte, higher capacity, etc., as shown in the top, are causing flash geometries to go down. And as the geometries go down, we get challenges such as shorter endurance, many fewer die to make the same capacity, which makes it challenging to get the same level of performance. Reliability decreases, the number of program erase cycles you get on a die, as you can see in the middle, goes down, and the error correction requirements keep increasing. And furthermore, we're faced with the issue that every vendor has a different type of flash, and the vendors change these types of flash quite frequently. The controllers have to keep pace with all that. So there's a growing dependence on the flash controller to close this gap and enable the latest generations of flash to get to market quickly. That's where the SF3700 flash controller comes in. It's been engineered to solve the challenges of NAND flash now and coming up. It's designed both for enterprise and client, and it has both PCIe and SATA interfaces in a single chip. It builds on all the award-winning technology and features of the current SandForce flash controllers, and we expect to have mass production of this in 2014. Now, if we look inside at the SF3700, you can see that in the bottom, it's composed of sort of three main units. There's a front-end interface, a core portion, and a back-end interface. Each of these portions has its own programmable control, enabling them to operate independently and to deliver very high performance and throughput. The front-end portion manages the PCIe and SATA interfaces. The core portion manages the flash translation layer, including some of our unique features such as our Dura-Write data reduction. And the back-end portion manages the very flexible flash interface that we have, and also our shield error correction and RAISE data protection. And we'll talk more about those in upcoming slides. Now, in terms of performance, we're currently at a stage of having early firmware running on the silicon, and you can see that we're able to achieve sequential read speeds that actually saturate the PCIe Gen 2x4 interface of the SF3700 and achieving over 1,800 megabytes a second. And compared to competing drives reported in the press, the speeds we're seeing with early firmware and also the specs that we plan to achieve are very, very competitive, if not industry leading. The goal being optimizing performance despite the flash geometry shrinking and all the challenges that we have to face, such as how to get this performance out of having fewer die in the system at a given capacity. Now, latency is another one of the key challenges for data centers, and getting predictable latency becomes harder and harder as NAND scales and we have fewer die and less parallelism. We designed the SF3700 and architected it initially to focus on that problem. And as you can see in the graph on the left, for the write latency distribution, we're able to get very tight bounds on the write latency, with 99.99% of the writes having less than 170 microseconds of latency, even in conditions of 70-30 read-write mix and very high queue depth. So this is a very good write latency distribution, very tightly bounded. We paid similar attention to read latency, and as shown in the graph on the right, even at the same 70-30 read-write mix, and this is where read latency tends to suffer because reads are impacted by getting scheduled behind die that are busy writing. We've managed to maintain very good read latency, and in particular, we have a very good trade-off of latency versus IOPS. And if you look at the equation on the bottom, there's a mathematical relationship between your IOPS and your latency at a given queue depth. Now, you can have competing drives that say they get lower latency, and as you can see in the blue curve on the right, a competing drive does have lower latency in some corners, but only at very low IOPS rates. As soon as you try to get that drive to do much higher throughput, it does not scale anymore in IOPS. It just maxes out. What we have in our SF3700 controller is a much more balanced solution that over a wide range lets you scale IOPS without increasing latency. In the SF3700, we've also made improvements to our Dura-Write data reduction system as compared to our previous generations. Dura-Write data reduction enables less writing to flash. That in turn has a number of recursive benefits because if we write less to flash, we extend the flash life, we increase the dynamic over-provisioning, how much spare space there is in the flash, reads and writes complete faster because there's less data, and those in turn generate a whole host of other benefits that sort of feed back on each other. Reduced write amplification also extends flash life, garbage collector runs faster, which gives you better performance, costs are reduced because flash life is extended, battery life increases, etc. So there are many, many advantages of Dura-Write data reduction, and they're improved in the SF3700. The Shield error correction technology in the SF3700 is the strongest SSD ECC available today. There are many new techniques we've used in the implementation, and we've applied for a number of patents on the innovations. Shield error correction technology uses hard decision and soft decision LDPC along with digital signal processing, or DSP. We use adaptive code rates in order to take the most advantage of the spare space in the flash and actually trade off, as we'll see, the amount of spare space needed for ECC versus the amount usable for user data. There's much hardware and much software intelligence to make this solution work, and LSI has proven LDPC experience because we've been shipping LDPC solutions in the hard disk drive industry for years. Now, the Shield error correction technology adaptive code rate works like this. If you look at how traditional flash would store user data and ECC, the NAND flash page is divided into a user area and a spare area for ECC. And virtually everybody else in the industry only uses the user space for user data and only uses the spare space for ECC, and partly that's related to wanting to keep everything in nice powers of 2 in terms of how you map data and where it lives. But due in part to the fact that we have our Dura-Write data reduction technology, we don't quite have the same constraints in how we draw those boundaries, and we don't really care if the user space is a power of 2 size or not. So early in life, we're able to take some of the ECC space when the flash is stronger and needs less error correction and use that for user data, which effectively increases the over-provisioning of the flash. That increase in over-provisioning can extend life and actually buy you much more longevity and or performance. And then late in life, as the flash wears more, we're able to do the opposite. If there are particular blocks that are much worse than normal, instead of just abandoning those blocks because we don't have enough ECC space to correct them, we can actually borrow from the user space, use more ECC, but only on the most problematic blocks, and keep more blocks in service. This also enables us to extend life of the flash in many cases. Raised data protection in the SF3700 provides for the highest level of data center and enterprise protection by guaranteeing that even if you have block failures in the flash or die failures, there is a way to correct it. So by using redundant parts of die or redundant whole die, depending on whether we have fractional rays or whether we have a full rays, we're able to correct from single page and block failures or even full die failures. In summary, the SF3700 is engineered to solve the challenges of NAND flash. In particular, we talked about how the Dur-Write data reduction enhancements provide higher performance and longer endurance, how the Shield error correction technology advancements provide higher reliability and also improve endurance, how the new raise protection levels and features provide more data protection and increase reliability, how the flexible and modular architecture is adapted to future flash and can deal with the problem of evolving flash types, and how the low predictable latency and high performance will help meet SLAs and provide performance even when there are less flash die in the system, as we're finding with newer flash geometries. Thank you very much.